Hello everyone, in this video we are just going to implement and demonstrate SPI, that is Serial Peripheral Interface Communication Protocol in Atmega16 microcontroller. Let's get started. As the initial step, I am just going to build the Proteus simulation circuit first for demonstrating the code that we are going to write. So I am opening the Proteus 8 professional software. Just click on this icon in the top left corner for entering into the schematic capture tab of this software. Here, firstly, we just want to pick the devices that we want to build for simulation. Just click on this components mode icon and then click on this P for opening the pick devices tab. Here, the first component required for our simulation is Atmega16 microcontroller. So here is the microcontroller. I am just selecting it by double clicking on it. You can see the microcontroller is selected. And other than that, we don't require any other thing for simulation. Just click on OK. I'm just placing this microcontroller in the schematic. You can see, just click on this, and once you make a left click in the schematic, you can see the layout of the component. Just place the component anywhere as per your wish. And further, we just require a SPI debugger for viewing the data that is being transmitted in the SPI bus of this microcontroller. So that can be found in this instruments tab. Just click on this icon right over here, and here in the list of these components you can see the SPI debugger. Just place this SPI debugger right over here, and that's it. Now we just want to connect the SPI line of this microcontroller with this SPI debugger. So as the first step, we are just going to transmit some data from this microcontroller SPI bus to this SPI debugger. And then we are just going to monitor the data that is being transmitted from the SPI bus of this microcontroller using this SPI debugger in the Proteus 8 Professional. So you can see the SPI pinouts of the microcontroller are this MOSI, MISO, clock and slave select. So PB4, 5, 6, 7 belongs to the SPI bus of the microcontroller. So we just want to connect all these pins for establishing SPI communication. So I am just connecting the MISO pin of the microcontroller to the data input of the SPI debugger, and clock to the clock of the debugger, and MOSI pin, that is PB5, to the data out of the debugger, and similarly the slave select, that is the SS pin, will be connected to the SS of the SPI debugger. So that's all about the connections required and the circuit required for simulation. As the first step, we are just going to write a program on this microcontroller for transmitting two different datas in different time intervals, and later we will be using another microcontroller for communicating it with this microcontroller using SPI communication. And for now, we are just going to write a program on this microcontroller for transmitting two different characters over SPI bus of this microcontroller. I'm just opening the Atmel Studio, which we are going to use for programming the microcontroller. In this Atmel Studio, just click on File, New, Project. Here select the C executable project and give a name for your project right over here, and select the destination folder right over here. I'm just choosing different destination. and then click on OK. In this tab, you just want to select the device that you want to program. In our case, the device is Atmega16A. Click on the microcontroller and click on OK. Now that the project has been created, you can see the project is Pro SPI and the main.c file has been automatically generated by the project that you have created in this Atmel Studio 7.0. And the first and foremost thing that we want to do is we just want to define the clock frequency required for our microcontroller. So I am coming to the top of the program and I am doing has define of f underscore CPU to be 8 megahertz. And later I'm just going to include another header file that is nothing but delay header file util/delay.h for using the internal delay available in the Atmel Studio 7.0 IDE. And nextly, coming into the programming part, the first and foremost thing that we want to do is we just want to define and configure the GPIOs required for the SPI communication. So here you can see there are 4 different GPIOs required for SPI communication. One is the slave select PB4, second one is the MOSI, which is nothing but master output and slave input pin, and the third pin is the MISO pin, that is PB6, master input and slave output pin, and the final pin is clock pin of the SPI communication, which is nothing but PB7. So in these 4 pins, you can clearly see that this MISO pin, that is the PB6, is the only input pin which receives data. Other than that, all the pins or all these 3 pins, slave select, MOSI and this clock pin of the master SPI device, will be configured as output. So I will be configuring this PB4, PB5 and PB7 as output and only this PB6 as input. So that can be done by writing to the DDRB register, right? Because we are just configuring the port B. So for configuring a particular pin as output, I just want to write 1 to the particular bit, right? So as I said, I'm just going to configure the PB4, 5 and 7 as output, right? So I'm just writing 1 to the PB4, PB5 and then I'm configuring PB7 as output. So PB4, PB5, PB7 has been configured as output in this line. Sorry, I just made a mistake. That is, this is not PB4, this is DDB4, DDB5 and DDB7. And finally, I'm just going to configure this MISO pin, that is PB6 as input. So for configuring a particular pin as input, I just want to write 0 to the data direction register for the particular bit. So I'm just writing 0 to that bit, DDRB ampersand equal to 1 left shift of DDB6. I have configured PB6 as input. And the configuration of GPIOs for the SPI communication in the Atmega16 microcontroller has been successfully completed. Now we are just moving on to the SPI control register and status register configuration. So for configuring this microcontroller SPI port, we just want to open the datasheet of the microcontroller. And then click on this SPI, that is serial peripheral interface tab, and going to the register section of the SPI port. And the first and foremost register is SPI control register. So here you can see the 7th bit is nothing but SPIE, which is nothing but SPI interrupt enable bit. So if we are using the SPI interrupt for receiving any data from the SPI bus, we just want to enable this bit. But for now, we are not going to use the SPI interrupt, so I am just neglecting this bit to be 0. And the next bit is SPE, which is the SPI communication enable bit. So for using and operating any data on the SPI bus of this microcontroller, I just want to enable this bit. So I just want to make this bit 1 for using the SPI protocol of this microcontroller. So in my program, I'm just going to do that. So the register that we are discussing is SPCR, which is the SPI control register, and I want to enable this SPE bit available in this register for using the SPI protocol of this microcontroller. SPCR are equal to 1 left shift of SPE. And nextly you can see DORD is the 5th bit. So when the DORD bit is written to 1, the LSB of the data word is transmitted first. And when the DORD bit is written to 0, the MSB of the data word is transmitted first. So usually in any communication, the data will be transmitted in this MSB of the data word first format. So I'm just leaving this bit to be 0. I don't want the LSB to be transmitted first in my communication. And nextly you can see the MSTR bit is available in the 4th bit format of the SPCR register. So this is a very important bit. You can see when this bit is written to 1, the SPI master mode is selected in the Atmega16 microcontroller, and when it is written to 0, the device will be configured as SPI slave. So I just want to configure my device as SPI master. So I am just writing 1 to this bit also in the same register. I just want to make the MSTR bit to be high. And nextly you can see in the 3rd and 2nd bit we are having CPOL and CPHA. So these two bits are nothing but clock polarity and clock phase selection bit for the SPI communication. I hope you remember the SPI communication protocol working explained lecture, where I have briefly described about these two features of the SPI communication and various modes of SPI communications based on the clock polarity and clock phase of the microcontrollers. So for now I'm not going to disturb these two things. I'm just going to use the SPI mode 0 communication by selecting these two bits to be 0 0, and nextly we are having SPR1 and SPR0 in the 1st and 0th bit of this register. So these two bits is useful for selecting the clock frequency of the SPI communication. Here you can see the table. When these two bits are having 0 0 and when the SPI 2x is having the value 0, F oscillator divided by 4 is selected. So in our case I'm just going to select F oscillator divided by 16. So F oscillator is nothing but the main clock 8 MHz divided by 16 will provide me, which is nothing but 500 kHz will be the SPI clock frequency. And for selecting this clock frequency, I just want to write 1 to the SPR0 bit of this register, and I want to leave the SPR1 bit to be 0. So I'm just writing 1 to the SPR0. And regarding this SPI 2x bit, you can see that is available in the SPSR, which is the SPI status register. So I just want to make this bit 0. So that is not a problem, because you can see it is having the initial value to be 0. But for ensuring that it is having the value 0, I am just making and writing 0 to that bit in the SPSR register. 1 left shift of SPI 2x, and that's it. You can see we have successfully configured the GPIOs required for SPI communication, and also we have successfully configured the device as SPI master, and we successfully set the SPI clock to be 500 kHz. And that's it. Nextly we are just going to write two more functions for writing and reading data from the SPI bus. So that I am just going to do above this main function. Firstly, I am just writing SPI write, which is the function required for writing the data onto the SPI bus. So for writing the data onto the SPI bus, the register that is used in our microcontroller is this SPDR register, which is the SPI data register. So it is a 8-bit register, so you can at the maximum pass data of 8-bit format on this SPI data bus. So I'm just going to write the data that I'm fetching to this function onto the SPDR register. You can see whatever I am passing on to this function is directly written to the SPDR, and later I am just going to wait until the write operation is completed. So whenever a read or write operation is completed in the SPI communication protocol of this microcontroller, this SPIF flag in the SPSR register will be raised. So you can see when a serial transfer is complete, SPIF flag is set. An interrupt is generated if SPIE is set. So I'm just going to wait here until the SPIF flag is set. So that can be done by writing while of SPSR ampersand of one left shift of SPIF. So here I'm just writing not. And that's it. You can see I'm just writing the data directly to the SPDR, that is the SPI data register, and once the data has been completely written to the SPI bus, this SPIF flag will be raised, and until it is raised I'm just waiting inside this while loop. So when the operation is completed, the program flow will be automatically exiting this loop and I will be getting the control back into my main program. So that is the logic, and the next function that I am going to write is the function that is required for reading the data from the SPI bus. SPI read. So for this, similarly what we did for write function, I'm just going to write the data 0xFF to the data register of SPI, and I'm just going to wait for the SPIF flag to be high, and once the flag becomes high, I'm just going to return the data register of SPI communication. You can see I'm just writing 0xFF to the data register of the SPI communication, and here I am just waiting until the SPIF flag is raised, that is when the data is completely read from the SPI bus, this flag will be automatically raised, and when it is raised, that means the data is readily available in the data register of the SPI communication, and once it is raised, the control will be exiting this loop and I will be returning the data register value of the SPI communication, that is SPDR. And that's all about the main two functions required for SPI communication. And now let's try to write a program for continuously transmitting two different datas from the Atmega16 microcontroller configured as master SPI device. So as the first step, what we want to do is, for sending any data from our SPI master, we just want to select the slave device to which you just want to send the data. So that can be done by pulling the slave select pin to low. So here in the slave select pin of the microcontroller, you can see there is a bar in the top of the SS, which means it is an active low pin. So for activating any slave in the SPI communication, we just want to make the slave select pin low, or we just want to pull the slave select pin low from the master. So we know the slave select pin is PB4. So for making it low, I'm just going to write 0 to that pin. And after that I'm just going to write SPI write of character A. sorry, this is not PB4, this is port B4, and after passing the data I just want to make the slave select pin high again for leaving the slave into the ideal state. And after passing the data I am just going to write a small delay of 1 second, and similarly I am just going to pass another data after 1 second, that is nothing but small b. Here I can see the programming logic is very simple. I am just pulling the slave select pin to be low and I am passing character small a, and again I am leaving the slave select pin to be high, and after that I am waiting here for 1 second, and after 1 second again I am pulling the slave select pin low and I am writing the data b to the slave device, and then I am releasing the slave select pin, and after that I am waiting here for 1000 millisecond. And since all these lines are written inside the while of 1, which is nothing but the infinite loop of the program, this process continues until the microcontroller is stopped. That is, for every 2 seconds the character A will be transmitted from the master Atmega16 microcontroller, and for every alternate 2 seconds character B will be transmitted from the master SPI device. Now let's test this code. I am just building this code by clicking on this build icon over here. You can see the build has succeeded, no errors found in our code. Now that the compilation is successful, let's try to test this program that we have written right over here using the Proteus simulation circuit that we have built right over here. So the programming logic is simple, right? In the first second we will be receiving this character small a data, and in the second we will be receiving this small character b data, and following that again we will receive in the first second a, b, and so on. So this process continues until the microcontroller is stopped, since all these lines are written inside the while of 1, which is the infinite loop of the program. So I am just loading the program onto this microcontroller. Here in the clock fuses, just select the 8 MHz as we have configured the program to be 8 MHz right over here, and click on this program file and go to the respective project folder of the Atmel Studio, and inside the debug folder you will find this hex file. Just click on this and click on open and click on OK. And now when I play the simulation by clicking on the play button in the left bottom corner of the window, you can see the SPI debugger pops up. So here are the data. You can see I am receiving the data continuously for each second. I am just pausing this. So from this sequence you can see this is the SS active means slave select active, that is SS pin has been pulled low and the 61 has been transmitted. So the light blue indicates the data that is transmitted from the SPI master, and the dark blue right over here is the data that is pushed from the slave to the master. So that is FF, and the SS pin has been made inactive. Again the SS is made active, and in the second I am getting the data 62. So these data are available in the hexadecimal format. So in the first second I am receiving the data 61, and in the second I am receiving the data 62. Again I am receiving 61, 62, and it goes on like this. So here is a table which represents the ASCII data into hexadecimal format and also in decimal format. Here you can see for the character small a, I am having the hexadecimal equivalent to be 61. And for the character small b, I am having the hexadecimal equivalent to be 62, and that is why I am receiving 61, 62 for each second. So our program is working fine, and it is transmitting the data a for 1 second and b for another second continuously, because we have written these codes inside the while of 1. And we have successfully configured the Atmega16 microcontroller right over here as SPI master, and we have successfully transmitted 2 different kinds of data onto the SPI bus. And now in the following video, I will try to configure another Atmega16 microcontroller as SPI slave, and I will try to read these two kinds of data from that slave microcontroller. See you in the next video. Thanks for watching.